For this question, we have a single span beam. It is supported at A by a fixed or rigid support, at B by a roller. It measures 8 feet in span. It is supporting a 2 kips per foot uniformly distributed load. Let's see if we can figure out the reactions for this beam and draw the shear and bending moment diagram. First of all, when we're looking at it, we recognize that this is not statically determinate, right? We have a total of 1, 2, 3 reactions, 4 reactions, but only one piece of beam. So when we check our R's against our 3 ends, we find that we're missing something, right? Not statically determinate. So the first thing I'm going to do is draw my free body diagram. And that's where I replace the supports for the equivalent reactions. So at A, I have a Y force, an X force, and a moment. I'm guessing at the directions of each of those. At B, in this case, I have a single vertical force. And just to simplify my life, I'm also going to come up with an equivalent point load to represent this distributed load. It is located right in the middle at the centroid. And I'll calculate it right now. It is 2 kips per foot times a distance of 8 feet. That's going to be 16 kips. Now that I have a free body diagram, I'm going to proceed with my equations of equilibrium, E squared. I can use them in whatever order I choose. I simply choose to use some of the X forces as my first one. From some of the X forces, I get that AX equals to 0. I then choose to use some of the forces in the Y direction equals to 0. And what I get from that is that AY minus this force plus BY equals to 0. Or written in a slightly nicer form, AY plus BY equals to 16 kips. Now I can't do anything else with this equation, so I'm going to park it and call it equation 1. Lastly, I have my moment equation. So I can do a sum of the moments anywhere I choose to. I'm going to do a sum of the moments about A. And I choose counterclockwise as my positive. And I'm going to identify, I'm going to do it about support A. So if I'm doing a sum of the moments about A, AX and AY don't factor in because the distance between those two forces and A is 0. This moment does appear because it's a moment already. It's not a force. So the distance, if you will, is baked in already. So first things first, left to right. The moment at A, I guessed it going in this direction, counterclockwise, which matches our positive. It's a positive moment. Okay? It's not multiplied by a distance. Left to right, I get moment caused by this equivalent point load. It's going to be that force times half the distance. So it's going to be that equivalent point load times half the distance, 8 feet divided by 2. And this moment is actually a negative moment because it's in the opposite direction with respect to A from what we assumed positive. Lastly, the moment caused by By. It's going to be a vertical force By times a horizontal distance of 8 feet. And this moment is positive because it's in the same direction as what we assume positive with respect to A. Okay? So this here is just a value at 16. So we can probably simplify this a little bit. So this is 64. 8. Okay, so the moment at A plus 8 times By equals to 64. I'm leaving the units out just to simplify things a little bit. Now I have two unknowns, but they don't match the unknowns in equation 1. That means this equation right now is not helpful. So I'm going to park it and call it equation 2. So now we're kind of stuck. What do? We have more unknowns than we have equations to solve them. And that's where our inflection points will come in handy, because it allows us to find those virtual hinges so that we may split the structure and come up with a new equation of equilibrium. In this case, let's see if we can find where the inflection point is. So this is our undeflected beam. What we have is a fixed support here, a roller there, and a distributed load that's trying to deflect it. So more or less, this beam kind of wants to smile, right? However, it's not a full smile, right? It's not allowed to smile completely because it must be straight, right? It's undeflected. It cannot rotate at the fixed support. So it comes down as a smile, but then it must frown enough so that it gets back to being undeflected at that fixed support. Okay? And what we've learned from our inflection point convention is that at 3L over 13 from a fixed support, we get an inflection point, right? Because it must go from a smile to a frown, or from a frown to a smile, depending on how you look at it. Make sense? Now, this L is the span, the distance between the fixed support and the nearest support you're considering. So in our case, it's 8 feet. So 3L over 13, or 3 times 8 divided by 13 is 1.85 feet. Which is great because now we have a hinge right there, right? Or a portion of the beam that behaves like a hinge. We can cut it, split it open, and not worry about any moments because the moment there is 0. So what do? We have a choice. We can cut right here and look at the left-hand side. We can cut right here and look at the right-hand side. It doesn't matter. If we do it correctly, it will solve the whole thing. But maybe one side is nicer than the other. I propose, in this case, how about we do a split here and look at the right-hand side, because that will bring By into it, which then we can put into here to get the moment. We can put into here to get Ay. Okay? So I take the right-hand side, but again, that's my personal choice. You can do the left-hand side and still rock it. Okay? So I'm going to draw the free body diagram, a little bit exaggerated maybe. And here at the inflection point, because we're opening it up, shear and axial forces are still transferred. But I really don't care what they're going to be because I'm going to do a moment about that inflection point, right? But it's still a good idea to practice this and make sure that they appear. This portion of the beam goes from the inflection point all the way to B. And how much is it? It's going to be 8 feet minus 1.85. That's 6.15 feet. And I think the last thing I'm going to do here is come up with the equivalent point load to represent this distributed load. This distributed load is only over 6.15 feet. So we must recalculate that equivalent point load. So 2 kips per foot times a distance of 6.15 feet. That gives us 12.3. Okay. So now, let's do an equation of equilibrium. I'm going to do the sum of the moments about the inflection point. I'm going to pick counterclockwise as my positive moment, and I'm going to put the inflection point as the location I've chosen. So some of the moments with respect to this point, I'm going to go left to right. These two don't appear. This force does appear in it, the equivalent point load of the distributed load. So that's going to be this equivalent point load times the distance of half this distance. And this moment is in the opposite direction as our positive with respect to the inflection point. So negative. And the last one is this one here, By, a vertical force times a horizontal distance. And this moment is positive. If I substitute the value of this equivalent point load in here and solve for By, I get that By is 6.15 kips. Because this answer is positive, that means that it's in the same direction as what I guessed in my free body diagram. In the free body diagram, I guessed that By was up. It means that this is up. Now that we have By, we can substitute into 1, then in 2 to get Ay and a moment at A. Let's do that. So we get that Ay equals to 9.85. And because it's positive, it's the same direction that I guessed, therefore up. And then sub into equation 2 to get that the moment is 14.8 kip feet. Because we're getting a positive answer here, it means that this moment is in the same direction I guessed in my free body diagram. Therefore, it is counterclockwise. So this is a good place to summarize the reactions. And now, after having figured out these reaction forces, I'm simply going to clear the board so we can do the shear and bending moment diagram for it.